Imagine two clocks, one on Earth, one aboard a spacecraft. You might think they tick in perfect unison, but what if I told you they don't? From Einstein's 1905 breakthrough to today's millimeter-scale lab tests, time itself bends with motion and gravity. Let's travel through more than a century of discoveries to see how and why time isn't the same for everyone. In June 1905, Albert Einstein published his paper on the electrodynamics of moving bodies. He proposed two simple postulates. The laws of physics are the same in every inertial frame, and the speed of light is constant for all observers. To illustrate this, he imagined a light clock, a light pulse, bouncing between two mirrors. If that clock moves, the pulse travels a longer diagonal path, so each tick takes more time. In other words, a moving clock ticks slower than one at rest. Fast forward to November 1915. Einstein unveils his general theory of relativity, describing gravity not as a force, but as space-time curvature. One dramatic consequence: clocks in stronger gravity fields tick more slowly. On May 29, 1919, Sir Arthur Eddington led expeditions to Principe and Sobral to photograph starlight bending around the Sun during a total solar eclipse. The observed deflection, 1.75 arcseconds, matched Einstein's predictions exactly, eclipsing Newtonian gravity and making Einstein a global sensation. In 1959, Robert Pound and Glenn Rebka at Harvard tested gravitational time dilation on Earth. They raised gamma-ray photons up a 22.5-meter tower and measured their frequency shift. The photons lost energy climbing out of Earth's gravity well. This gravitational redshift confirmed that clocks deeper in gravity tick more slowly. October 1971 saw Joseph Hafele and Richard Keating fly 4 cesium beam atomic clocks eastward and westward around the globe. The eastward clocks, moving with Earth's rotation, lagged behind identical ground clocks. The westward clocks, moving against it, ran ahead. The discrepancies matched relativity's combined predictions for motion and gravity. Since the late 1970s, GPS satellites orbit at about 20,200 kilometers altitude and cruise at approximately 3.9 kilometers per second. Two relativistic effects act on their onboard clocks. Special relativistic time dilation slows them by approximately 7 microseconds per day, while weaker gravity at altitude speeds them up by approximately 45 microseconds per day. Engineers pre-adjust these satellites' clocks by roughly 38 microseconds each day. Without that correction, your smartphone's position would drift by kilometers every day. In 2021 to 2022, JILA physicists took relativity to the millimeter scale. They placed 2 optical lattice clocks just 1 millimeter apart vertically and measured a fractional frequency shift of 1 × 10⁻18. Even over that tiny height, gravity made one clock tick measurably slower than the other. These experiments not only reaffirmed general relativity's predictions, but also paved the way for ultra-high-resolution geodesy and new tests of fundamental physics. From Einstein's 1905 light clock to millimeter-scale lab tests today, over a century of experiments proves that time bends with speed and gravity, and that bending is at the heart of technologies we use every day. So next time you check your watch, remember, time is never quite the same for everyone.